Welcome everybody to the invited talk of Andreas Huelsing. Andreas is a professor at the University in Eindhoven, and today's talk is going to be about Hashbase signatures, about the history and challenges. So Andreas is the lead submitter on Sphinx, which is a Hashbase signature, and he's also a designer of XMSS, which is already a standard in the IETF, well, with the CFIG, and with NIST. So Andy, I'm very curious to hear what you have to say about the future challenges for Hashbase signatures and how we got here. Thank you.
So thanks, Tanya, for the introduction, and thanks for inviting me. You know how this is, you're asked to give a talk, and then you propose a title, and then you think like, actually, I should have maybe done something different the moment you start preparing the talks. I will briefly go over the history of Hashbase signatures, but then go more into the recent history and especially discuss some challenges that drove my work over the last years. So I will cover some background, then I will discuss the constructions, trying a different approach in previous talks. So I hope I cover everything. If you want a bottom-up approach, you might want to have a look at summer school talks that I gave before. I'm now more looking on a high level, and then I will look into two issues in security related to Hashbase signatures that got some attention. One of them actually got the Best Paper Award at this conference, and the other one got the person or one of the people that founded a position as PhD student with me, so and also got some publicity. And then I will afterwards look into further challenges or next steps that I see or that I was working on with people. Okay, so I think the background of having this talk is that we have Sphinx Plus, which, as Tanya mentioned, is one of the 3 signature schemes picked by NIST to be standardized. And well, I might be lead submitter, but this was a team effort with quite a huge team. And in addition, there are already 2 stateful Hashbase signature schemes. So these are schemes where the secret key has to change with every signature, called XMSS and LMS. And these have RFCs by now within IRTF. And are also covered by a NIST special publication, and so they are standardized by now. So in general, Hashbase signatures are somewhat the conservative choice if you want to go for signatures, because you only need a secure hash function. So if you consider any signature scheme that can efficiently handle arbitrary length inputs, then this usually includes a hash function. I'm not aware of any efficient other way to do this. To compress the message in the beginning. And the security properties you need from this hash function are sufficient to build actually a full-fledged signature scheme without needing any additional mathematical hardness assumption, which is used in all the other schemes, like if you look at lattices or queue-based schemes, or recently the code-based attempts. And when it comes to performance, the schemes have somewhat fast verification, so especially the stateful schemes are actually really fast in verification. And they also have pretty small keys. So we're talking about 2 to 3 hash values, actually two hash values in general. So this is about the smallest public keys you can get, and the secret keys can be really small, but for the stateful schemes, you sometimes want to keep some additional state to speed up implementations. But the secret part is actually really just 1 or 2 seed values. Okay, so how do these schemes work? So Lampert in, I think, 76 figured out that a hash function is all you need to build something called a one-time signature scheme. So a one-time signature scheme is a signature scheme where I can use a key pair to sign exactly 1 message. And so the most basic case of Lampert, if I want to sign 1 bit, looks as depicted here. So you have 2 secret key elements, which are just random bit strings. The public key consists of the hashes of these two values. And to sign the bit 0, I publish secret key 0. And to publish key 1, I publish secret key 1. And this might already tell you why this is a one-time scheme, because if I sign the two possible messages here, then I immediately know the full secret key. If I want to sign m-bit messages, I just take m of these pairs and follow the same protocol for each message bit. And then you see also that if you learn more than one signature, then you can start to sign quite some more messages usually. Okay, so this gives you a one-time signature scheme. There are more efficient versions, namely Winternets, which I will discuss a bit later on some level of detail. But a one-time signature scheme, of course, is not that useful because you can only sign once. So Merkel proposed what we now call the Merkel signature scheme design, which is a stateful design, which uses a Merkel tree to authenticate the public keys of 2 to the h one-time key pairs, and turns thereby a one-time signature scheme into a many-time signature scheme. And while I do not go into the details how this exactly works, the tricky part here is that you have to, of course, only use each one-time key pair once. And for that reason, these are used like one by one. And usually we just put some order of them, say from left to right, and use them. And so we have to store which ones we already used. And this is a principle used in Merkel's original scheme, in LMS and XMSS, as well in Pyramid, which is a recent proposal which follows the design decisions made in Sphinx after XMSS and LMS were standardized, and essentially is overlapping with Sphinx on everything that can overlap. And you will see this is quite a bit. So if you look at this design, then as we increase the number of signatures, so which means essentially the Merkel tree height h, and thereby the number of one-time key pairs that we're authenticating, the secret key size goes up significantly because we have to store all the one-time secret keys. The key generation time goes up significantly because we have to generate all the one-time key pairs and then compute the tree on top. The public key remains the same independent of the number of signatures you can do with such a key pair. The signature size goes up logarithmically in the number of signatures that you're doing, so this is pretty fine. Similarly, the signing time goes up about logarithmically in the number of signatures that you can do if you use the right algorithms for this, and verification time too, but is like in absolute values not as much hit as the signing time. So most of you notice, of course, or might have seen this, the size increase in the secret key is not really an issue because there is a generic construction using a pseudorandom generator to turn any signature scheme that has a long secret key into a signature scheme that has a short secret key at the cost of always first expanding a short seed using the PRG to get the long secret key out of the seed. And if you apply this to the scheme, and this is what I will from now on assume for all the schemes to be applied, is the secret key can be shrinked to a single seed value. And the performance impact is just that the two operations which take a secret key, namely key generation and signing, actually first have to call this PRG, which can take a moment. But there are ways to do this efficiently, so let's ignore this for now. So this leaves one issue actually in terms of performance, namely the key generation time. And the way out of this is the hypertree approach, which is relevant if you want to build a stateful signature scheme which can handle a lot of messages. And and is also relevant for the stateless signature schemes, because there we need essentially an M-time signature scheme where we can generate, kind of have to run key generation every time in some sense. And so the idea here is that you build something which I think first was called a certification tree, then we called it a hyper tree, which I think was Tanya's idea, in the Sphinx proposal, and some, for XMSS we called it a multi-tree. I don't remember what LMS is calling it. And the idea is you take some M-time signature scheme, and then you use it to sign the public keys of M further instances of this M-time signature scheme. You use those in turn to sign M key pairs of this M-time signature scheme, and so on, until you arrive at the bottom layer where you use the M-time signature schemes then to sign the actual messages. So this is essentially something like a huge PKI, and it gives you an M to the D-time signature scheme if you use the layers of key pairs, right? So how does this behave? If I compare this like to an M-time signature scheme that uses the previous approach that allows you to sign the same number of messages, then secret key and public key size are essentially the same, especially if I use the trick. The secret key size is exactly the same, and the public key size too. The key generation time goes significantly down because I only have to generate the top level tree actually during key generation. If I want to be efficient, especially for the stateful schemes, then I actually have to generate the leftmost key pair on every layer during key generation. But this is still going from exponential to linear in M. And in addition, the signing time gets a bit of a speed up because I do not have to compute all the sub-leaves of a node to actually compute it. I just have to generate the key pair essentially that it's part of, which makes computing authentication path nodes, which I didn't explain, but the nodes in the Merkel tree that you have to put in a signature cheaper. The impact is that the signature size on the other side goes up because about the previous approach having one-time signature, which is significantly larger than a hash value, and then a bunch of hash values in a signature. I now have D one-time signatures in there. And this also means that verification time goes up because I actually have to verify all these one-time signatures which are in the signature. And in terms of state, it's still the same. I have to use these many times signatures of a member, which I used how many times, and they are stateful themselves. So I do exactly the same. I'm using them in some order, say from left to right, and have to remember where I am. Now, this is a first step to actually go to stateless signatures where I don't have to store any state, and my secret key just remains the same. And the first mention that I'm aware of doing this somewhat efficiently is Goldreich's proposal. There was a previous work by Nauer and Young, but the one that's closest to what we later do is this one, where you take a many-time signature scheme and then you take a random source and you just pick a random leaf to actually sign your messages. Alternatively, you can also just use the message as an index in the tree and use the respective leaf or index of the many-time signature scheme to sign your message. And this actually gives you a stateless signature scheme. There are just two catches. So on the one hand, Goldreich proposed this using a hypertree of one-time signatures. So you get a certification tree of one-time signature key pairs where you take, on the top level, you take a one-time signature scheme to sign the concatenation of two one-time signature key pairs, and so on. So you get a binary tree of one-time signatures. And this means that your signature size goes up. And it goes up significantly because to get a signature scheme that can answer Q signature queries, you need a many-time signature scheme that can do 2 times the security parameter times Q squared signatures. And this is quite large. So if we want to do something like, I don't know, 64 signatures, 2 to the 64 signatures, you end up with about a tree height of 128, and this times the security parameter. So this gets a mess. There might be some optimizations in terms of the size, but you end up at least with a tree height of something like 256, because you have to prevent index collisions, right? And so this means that you can do this asymptotically efficient, but if you look at the specific proposal, then the signature size grows up significantly because you have like 256 one-time signatures in this example. Your verification time goes up almost as badly because you have to verify all these during verification. The signing time is not that much worse. It's if you would have a stateful scheme which can do as many signatures as you can do with this one, then you don't need that much, or a tree that's as high as the tree here, and therefore this will be still cheaper, but the difference is not that significant, I would say. But this was an asymptotically efficient proposal where you have actually polynomial runtime of the different algorithms. So this was already quite an achievement. And the Sphinx design actually built on this. And the core idea here is, I think, due to Daira Hopwood. So this was something that was developed in the Tau Loves project by people that we then joined. And they proposed to actually use a few times signature scheme in combination with a many times signature scheme. And so the idea would be not to use the many times signature scheme to sign messages directly, but you actually use them to sign few times signature key pairs. So a few times signature scheme is a signature scheme that you can use to sign a small number of messages, say 7, 8, 9. And if you sign more with this, it does not immediately collapse in terms of security, but it just starts to degrade slowly. And so this means if I'm now doing kind of approach by Goldreich, just what we did not sample a random index, but we computed it as a pseudo-random function call of the message to be signed and some secret key element. Then you just have to make sure that the key is large enough that an I times collision on the same few times signature key pair does only happen with sufficiently small probability such that the product of this multi-probability and the probability of forging a signature after seeing that many signatures using the same few times signature key pair is negligible. And to make this thing efficient, we built the multi-time or the many-time signature scheme using this chain of constructions we had before. So we start from one-time signatures, use a Merkel tree to build a many-time signature scheme, and then use a hypertree to build a many-time signature scheme where key generation doesn't take too long, and especially it doesn't take too long to build a chain of signatures that authenticates one of these few time signature key pairs. And this gave us actually an efficient stateless signature scheme. So if you compare this to Goldreich, then key generation time slightly goes up because you do not have to generate just one-time key pair, just one-time key pair, but one of these Merkel tree transformed or these many time signatures that you obtain by using the Merkel tree. The signing time goes a little bit up because you actually have to compute trees on the path from the leaf to the root instead of just one-time key pairs. It might even be the same or a bit less. I never actually computed this in detail. The important thing is the signature size goes down significantly, and the reason is that we do not have that many layers, and the few time signatures are not that large in comparison. And most importantly, we can use a many time signature scheme which can or just has to do significantly less signatures than in the case of Goldreich. And for a similar reason, then the verification gets also faster than for Goldreich because the path that you have to verify is not that long. And so, yes, the main trick here is actually that because of using these few time signatures, you can use a smaller many time signature scheme. Okay, so that far as a background. Now I would like to go into, as I said, two topics in security that have a maybe not the best history in this context. And the first thing is the tight proof challenge. So for these schemes, it's actually not too hard to prove non-tight security. So this is something you already know since, depending on the schemes, like for Sphinx, we did this immediately. For the Winternet's one-time signature scheme, which is a signature scheme a bit more efficient than Lampert's scheme, and it's actually kind of the central thing here. We had non-tight securities proofs at least since 2006. I think there was a paper by Michancho and Hevia from 2004, which slightly modified the construction but gave a security proof. And then there's a paper by Doth, Smart, and I'm sorry, I currently don't get the third name, Stam, that that gave essentially a proof that we're using now. And this is was a non-tight proof. But what we actually want in terms of tightness is we want that if you use an n-bit hash function to construct a scheme, you want n-bit security. And so in their cases, you take an n-bit hash function and you get something like n over 2-bit security. And for Hashbase signatures, this is not only a theoretically not so beautiful result, it also means that you have to increase the size of your hash values that you're using by a factor of 2. And this doubles your signature size by a factor of 2 because your signatures just consist of hash values. So this is really a practical issue. Now, to get a tight security proof, there are two preconditions or two challenges that have been solved before quite efficiently and to a satisfactory state. So you cannot rely on collision resistance. So you need collision resilience, because if you have trouble with collision attacks, then you have birthday attacks, which means that to achieve n bits of security, you need 2 n-bit hash values, so you get exactly this factor of 2. There was this MSSSPR paper from 2008 by Damen Takagi, and I'm really sorry, I don't remember the other two names, which showed how to build a Merkel tree without collisions or without relying on collision resistance. There is a paper by myself about Winternets, how to do this without collision resistance. There was a previous attempt on this using PRFs in 2011 that I was involved in, which the the proof actually failed. So the proof turned out to be non-sound. And of course, there is Lamport scheme, which doesn't need collision resistance. So that's an alternative, but it's less efficient than Winternitz. And then the last component that you have to handle is the message compression. And there is this enhanced target collision resistance proposal by Halevi and Kravchik, which was meant as an alternative for hash functions used in hash and sign. And so this gives you message compression without relying on collision resistance. So for these three steps, we can actually do what we want to do without having to rely on collision resistance, and that turns out to be enough for the full construction. Now, if you do this, you run into the next issue, and this is that you're now relying usually on not usually, like in general, on targeted security assumptions. So you're relying on things like second pre-match resistance, one winners, and so on, where you're given a specific target on which you have to operate, right? So on one winners, you're given an image of the function, you're asked to find a pre-image of this. Now, as I said in Sphinx, for example, or also in XMSS, your signatures consist of a bunch of hash values. And if you get a lot of signatures, then you get a lot of hash values. And you will actually win in some sense if you find a pre-image for any of those. And so if you have T targets, then an n-bit hash only gives you n minus log T security, because the probability just by random guessing inputs to hit one of your targets loses you a factor 2 to the T in the complex factor T in the complexity. Now, this is a problem, but this was solved on the one hand for XMSS in 2016. There we proposed kind of a standard model domain separation approach that solves this. And actually already in 1993, this was solved by Leighton and Micali, where they propose domain separation in the random oracle model to prevent this. The reason that this was hardly ever caught in the literature up to recently, essentially when the Cisco people started to write the LMS RFC, is that this was never published as a paper, but only written as a patent. And so just as a side note, these people never complained about this. But if you want scientific credit, maybe write good papers that people cite and not patents, and then you will get the scientific appreciation. You might not get the money, but if you're patenting crypto, well, usually you also don't get much money because your scheme will just not be used. So just don't write patents, write papers, and everyone's happy. So why was I talking about these? So these are the solved issues. This leaves essentially one challenge, and this is a challenge in the security proof of Winternitz. So as I said before, you can either use Lampert, then you get large signatures, or you use the Winternitz one-time signature scheme. And this has quite a challenging proof, and the proof is related to hash chains that Winternitz uses. And you don't have to understand in detail how these hash chains are constructed. What you're actually doing is you're computing a chain of nodes where you start with the secret key or with a secret key value. Then you do some pre-processing using some auxiliary input information. So this, for example, is usually where this domain separation is implemented. And then you apply a hash function, and that gives you the next node in the chain. You again do this pre-processing, apply the hash function, which gives you the next node in the chain. So here, C2. And you do this W minus 1 times, where W is a system parameter called the Winternitz parameter. And this gives you a chain of W nodes, where the first node, index 0, is the secret key element, and the last node is a public key element. Okay, and I will not go into detail of how these chains are actually used. But I want to talk about the inversion security of those. Just as a side note, you might have seen in recent papers, we started talking about tweakable hash functions, and tweakable hash functions are just an abstraction which combines this pre-processing and this hashing into a single function. So this takes the auxiliary information together with the input that you want to hash and hashes this. And this auxiliary information, in this case, is called tweak, and actually the public parameters. So we're just putting a black box around this to hide the details in the analysis. And I will actually also hide this now, because for the following, it's just irrelevant. So the adversary's task in this case to break the scheme can be boiled down to the following. We generate a chain of length w minus 1. This happens during key generation. Then the adversary is given the last node of this chain. Afterwards, the adversary is allowed to pick any position in the chain and learn the node at this position. So say C2, for example. So the adversary would send 2, gets back C2. And then the adversary, so this is what happens during sign. And then the adversary is asked to come up with a B prime, which is smaller than B, and a node CB prime, such that if I complete the chain from CB prime, so I do the W minus 1 minus B prime hashes, I end up at the public key. Right? So this is essentially, I'm getting the end of a hash chain of a certain length that I determine as adversary, and then I'm asked to find a longer hash chain which ends in the same node. And so this computation is what happens during verification, because in Quinternets you're given such an intermediate value of a hash chain, and during verification you check that this actually ends up in the public key. So let's see how such a longer chain could help us to solve some problem that we're interested in. We know that the last nodes agree. So for that reason, these chains must collide at some point, right? So by the pigeonhole principle, we know in the end they collide. So they might only collide there or earlier. Let's say they collide at this iteration B plus 2. This means that the nodes at position B plus 1 actually form a collision, because applying the hash function to both of them ends up in the same value. And more specifically, the node in the chain provided by the adversary, so the longer chain, actually is a second pre-image for the upper chain. And this is something we know how to extract, and we can be happy with this. There's a solution. Everything is beautiful, and we can do this tightly. We get a tight proof. Great. The messy situation is if the following happens: if actually the adversary's chain ends up to be a pre-image of the first node in the chain that we have given to the adversary. So in this case, this node is a pre-image. And now the problem is that the reduction actually has to guess this position B if we want to place a pre-image challenge in this node such that the adversary solves this for us, right? And I will later come to one option how we might prevent this, but in general, it's kind of hard to get around this. And why is this a problem? I mean, guessing B, that's something like we do in many reductions. There's even like plug and pray argument. This is really done a lot. The problem is that this generally has to be guessed for every chain. And if you look at typical Sphinx Plus parameters, for example, then we have 67 chains per Winternet's key pair. And we have about 2 to the 60 Winternitz key pairs in the whole Sphinx Plus scheme. This means the probability of guessing correctly for all these key pairs is smaller than 2 to the minus 64. This translates to a reduction loss of 64 bits, which is quite painful. So you're losing 64 bits of security in this case. So one solution that we proposed together with Mike Kudinov, a PhD student of mine, which will appear at Easycrypt now, is a way to handle this in the case of Sphinx Plus. So in this case, you can observe that the Winternitz key pair here is actually only used to sign user-controlled messages, because we're building this this hypertree where internally the many-time signatures are just used to sign the public keys of further many-time signatures, which are generated by the user during key generation in theory. And at the bottom layer, we're using it to sign the public keys of few-time signature schemes. So these are all not adversarially controlled messages. And for that reason, security under non-adaptive chosen message attacks is actually sufficient for Winternitz in this scenario. This still gives us a factor W loss in security, but this is really a factor W for the full Sphinx construction. So in total, you're losing log W bits of security. So if W is 16, you're losing your 4 bits. This is something we can live with. And the reason for this loss, why this is still there, is that we have to argue that the challenges that we're placing at these positions in the chain behave like the bth node in a chain. And I will not go into the detail why this is hard, but this is where this loss comes from. What's a bit annoying is that in some sense, this also works for XMSS. But in XMSS, the messages are signed, the messages which are signed are chosen by the adversary. And this means we have to play some tricks to actually make non-adaptive chosen message attacks security sufficient. And the trick that we're playing is we can use CMA, so chosen message attack to no message attack reduction, which you can do in the QROM. And we can do this with modern techniques. So we had a paper last year about this, which shows that this works. The problem is you essentially end up with a QROM proof, and you really need strong properties, like you need to do reprogramming in the QROM. So this is not really what we would like to have. So for Sphinx, this proof is actually really nice, and there's nothing funny you have to do there. But for XMSS, let's say it's unsatisfactory what you get out of this. And so there is an alternative approach that I looked into quite a lot, but that I didn't get working. So actually, this is where this flaw in the tight security proof of Sphinx was found in 2016 or 2017, briefly after the start of the NIST competition. So an idea that we looked into in the 2016 paper about XMSS, because it's just hidden in Winternitz, which is also used there, was, well, if we would use second pre-image resistance, then we can actually place second pre-image challenge, and we will know pre-images. So the idea is this pre-image at the same time is usually also a second pre-image for the node that we use to compute this chain, at least with some probability, because if this this node in position B has at least 2 pre-images, then the adversary will give you a different node than the one that you use to compute it, with probability at least 1/2. Because which one was used by you that's what we thought, information theoretically hidden. This argument actually breaks down if you notice that this node that you used, like this gray node, is actually the output of some hash chain computation. And then it actually becomes hard to reason that the adversary really has to give you a second pre-image with high probability and not the node that you already know. So for b equals 1, this is no problem, because then this is really just a random value. But if b is greater than 1, we currently do not know a tight proof. We know a non-tight proof, but not a tight proof that A will actually have to give us a second pre-image with high probability. So this is actually a nice open problem. If you have any idea how to solve this and come up with a tight proof that this second pre-image or reduction from second pre-image resistance works here, let me know, write a paper about it. I'm pretty sure that you have good chances to get this published in a nice venue. But at the same time, also a warning, this is not an easy problem. So this was the one thing that that was bugging me quite a lot. We solved it partially, at least for Sphinx Plus, and it would be nice to have a nice proof for XMSS2. The second problem is the problem which the NIST team actually figured out, or rather Sidney Antonov proposed, and then they showed how to actually exploit it. And this is the issue with some of the tweakable hash function instantiations using SHA-2 256. And what I want to talk about is especially why we did not catch this. So a brief summary of the issue. There is a talk about this which you should watch by the Sphinx team, but Sidney noticed that some of the SHA-2 256 constructions of the tweakable hash functions do not achieve security level 5 with regard to the necessary properties. Especially, it's possible to break the multi-target attack mitigation technique. And so you lose about 40 bits of security in this case. And the core reason for this is that the chaining value in SHA-2 256 is too small. So the internal value that's used in Merkel-Damgard and moved forward from compression function call to compression function call is just too small. And this allows for some long message second pre-image attacks, which exploit that finding collisions on this chaining value is cheaper than finding second pre-images. As I said, for details, have a look at the NIST talk. But this is an issue in SHA-2. And the solution is pretty easy. You have to use a function with a bigger chaining value if you want to achieve sufficiently high security. And so we immediately fixed this by using truncated SHA-2 512, which has a 512-bit chaining value instead of a 256-bit chaining value for these problematic instances, and thereby it's solved. What of course is that we didn't figure this out before. So why did we not see this? I mean, we had security proofs. Why did these proofs not fail? And they didn't fail in this point. The reason is that if you look at what's covered by our security proofs, then I do not have the time to go through all of them, but actually what you see here in the right corner is we stop at what's called a keyed hash function. So we show how to construct from a keyed hash function, a tweakable hash function, and then how to bootstrap from there to all these building blocks that I talked about before. But for the keyed hash function, we just assume that SHA-2 and actually Shake are good keyed hash functions. And we show that if they are good keyed hash functions, then we can show via quantum information theory that there are certain bounds applying in solving the properties that we require from them. So this is then the QROM. These bounds really just apply if the functions behave like good functions. And then you get all these beautiful bounds. The problem is, if they are not behaving like good keyed hash functions, well, then these don't apply. So this means, in short, our proofs stopped actually too early. And so the second open problem, which I think would be nice to have people working on, is a security analysis of Merkel-Damgard and sponges for the properties that we need, especially targets. So we now have solutions which we think work, but to some extent they are also like really putting out the big guns and just doubling the chaining value, while we do not know what's actually required there. So this is a second open problem that would be really interesting to see results on. So I think I got only a few minutes left. So I want to briefly cover the next steps that I think are important on this topic. The first thing is, and I think Peter will talk a lot more about this tomorrow, but we've seen there were some parts where our proofs just didn't cover things. And there were actually, in the case of Sphinx, really, and XMSS, there was a mistake in the proof, not in the actual security bound, but in the proof. And in general, it seems like these proofs of security for post-quantum crypto are getting more and more complicated. We make use of new tools, which we are not that familiar with. We have less or fewer knowledgeable reviewers. And so in consequence, this whole business gets more error-prone. And this also reduces confidence in the schemes. I mean, I had some debate with the NIST team about how they publish their result, because I think like every time we have something like this actually decreases confidence. But of course, this is also our fault because we publish proofs which turn out to be wrong and or fall short in what we analyze. And one solution to this, at least to overcome the issue of faulty proofs, is just to use computers to verify your computational proofs. And this reduces then the verification effort to just verifying the actual statements which are proven. And this is work that I'm doing with my PhD student, Matthias Myers, and now Microsoft decided it kicks me out of my talk. So give me a second to get back into it. Yes, so this is something I'm working on with Matthias Myers, who previously also worked with me on, or he mainly worked on verifying the security proof of Saber. And we're currently working on verifying the security proofs of Hashbase signatures in Easycrypt. And so what we already got is a verification of the traditional Merkel signature scheme, so just the schoolbook version. We are currently finalizing the proof, the proof of XMSS. So especially we already did the verification of this tricky business with the hash chain. So the new security proof I did with Mike actually seems to be sound. And the next thing then is to extend this to Sphinx. The paper is coming soon as being spoken by a researcher, so hopefully still this year, but we're working on it. The second thing I want to briefly catch is the topic of Sphinx plus C, which I also will write in a message about to the NIST mailing list as soon as I have time. And this is kind of the thing where you thought you're done, and then people come up with actually a great idea, and you think like, how could we have made this? So the idea actually is by Eyal Ronen and Elon Yogev. So they wrote a paper about this, and then later on asked Mike and me to join and and work out a bit more the analysis. And so they had an idea which allows you to reduce the signature size of Sphinx Plus by up to 20% at about the same signing speed. And it also allows new trade-offs between size and speed. So this is really just the 20% for if you use exactly the same parameters. but you might want to use other parameters which give you better trade-offs for your use case. The full paper can be found on ePrint by now. And I just assume that Tanya will abort me and tell me to stop when I don't have time anymore.
You're still doing okay.
Okay, then I will briefly explain the core idea of this. So to understand how this works, you have to understand how Winternets works and where these B values for the chain come from. So which position I'm picking. And these values come from encoding the message hash. So you hash your message to obtain a message B. And then, for example, in case of Sphinx, you mostly have W equals 16. Then you take your message hash and you take every 4 bits. So you take the first 4 bits, interpret this as an integer, you get a number between 0 and 15. You take the next 4 bits, interpret it as an integer, you get a number between 0 and 15. This gives you B1, the previous one B0, and so on until you encoded all of them. And in a second step, you're computing a checksum. And never mind how this checksum works, the important thing is you have to add this checksum to ensure that the forger actually has to invert one of the hash chains. Right? So after seeing a signature, when it comes up with a forgery, one of these chains has to be longer in like one of the chains you can obtain from the forgery. So an alternative way to do this, and in general, the idea we also thought about in the Sphinx team, just couldn't see how to make it work, is you encode your message such that these B0 to B lang 1, which is the number of Bs that you need to encode your message, that they sum up to the average value. So you just take 15 times lang 1 over 2, and you want to find an encoding B which just sums up to this value. Now we thought about complicated functions to actually map to such sets B by just expanding the message maybe or something like this. And the nice idea of EL and Aeon, where you actually just hash together with the counter, like hash your message together with the counter, and eventually like you increase the counter until you find a message which maps to such a nice encoding, which has the right sum, and then you can just omit the checksum. Right? So this means first you can remove the checksum, which removes 3, in case of these parameters, out of 67 hash values from the signature, which doesn't sound much, but you can do this for all the Winternet signatures in the Sphinx signature, for example. And you can go further. You can actually also remove further values if you limit the last x values of this vector B to be 0. So if we agree that a certain value is 0, then we do not have to publish a chain value for this one. We just don't even have to use a chain for this one, because this is fixed to be always 0. If it's not, we know that there's something wrong with the signature, and verification fails. And this last trick actually allows you to compress quite a lot. And exactly the same trick also works for force, which is the few-time signature scheme used in Sphinx Plus. And for both cases, you just have to increase the counter until you find a value which actually has this property, like a message which maps to this such a vector of B, and then you're done. Now, because you're searching, your runtime becomes variable. But actually here, it's important to note, because they actually got this in a review. It's variable time, but it's still independent of any secrets. So this doesn't allow for side channel attacks. The name constant time is just a bit unlucky in terms of this term. But it has a runtime which is independent of the secrets, but variable. Now, this variable runtime on average is actually faster than, at least for many parameters, than the original Sphinx runtime for these parameters, because you have to compute less chains and have to compute less trees in terms of force. But it has some variance, and the variance depends on the parameter. So you can see the paper for an analysis. In general, the variance, especially for winternets, is quite low, but you can actually optimize for it. So you can just decide how much variance you can take. If you're fine to have every 1 millionth signature, maybe have to wait 30 seconds instead of 1 second. Or if you really want the variance, which is at most a factor 2 of the original running time, you can select this, and then you get parameters which maybe compress a bit less. So I hear that Tanya just unmuted. So I will go to conclude. In general, Hashbase signatures are still the conservative choice. There are still topics to be solved. So it would be nice to have a tight proof for this adaptive hash chain one-wayness problem that I mentioned first. It would also be nice to have an analysis of Merkel, Damgard, and sponges for these advanced properties that were used in XMSS and Sphinx. It would be even more amazing if someone came up with a more efficient one-time signature scheme or few-time signature scheme. As we've seen, there are still optimizations which we just didn't think of. Especially I myself are probably just blind by looking at this for too long. And the really last point is these stateless and stateful schemes, as I said before, share a lot of code, especially in verification. And so I actually think a combination of the two could further optimize performance. So you can think about a system where the CAs, for example, use stateful signatures, which are smaller and more performant, and only the end users use stateless. This needs a stateful scheme which agrees on all these parts, especially in verification, with Sphinx Plus, and this is actually Pyramid. So it might be nice to standardize this one in addition. Thank you.
Yeah, thank you for the talk and lots of nice pictorial descriptions. We actually do have some questions on the Zulip channel, so let me read them out for you. So Fabio Campos is asking, well, first saying, hey Andy, thanks for the great talk. What do you think about having two somehow similar stateful hash-based schemes like LMS and XMSS? Do you see any disadvantages, or do you even see no suitable use cases for the respective scheme?
Tanya, can you mute yourself while I'm speaking, because I'm hearing myself?
I'm sorry, I can't.
Okay. I think this is a question of what you want. If you look at Sphinx, essentially we are reflecting the same combination. So we're having the robust and the simple parameters, which are essentially simple as what LMS does, just a bit different, and robust is what XMSS does. By now, I'm pretty confident that the simple parameters are fine. And so this approach that LMS takes is fine. But I think for this, it would be good to closer look at how the hash functions that we're using are actually working, and if they actually really give us the guarantees that we like. And then we can also trust these parameters, I think. So I think in general, the simple ones are nicer because they are more performant. But there are still some more gaps than for the robust parameters in the proof. And I think by analogy, they should be fine, but that's by analogy.
Okay, thank you. There's another question by Mohammed Guduwan. and also congratulating you on the thanks for the nice talk. I want to ask a question about how the limits of Sphinx Plus parameters. Is there any particular upper limit for the parameters, especially log T and K? The official submission suggests the parameters log T and K being 12,14, 633, etc. until 9,35. This means we need message digest functions which output digest with output lengths 168, 198, 315. Would we choose those, log T, K, much larger, for instance, 20,50, requiring a hash function with output of 1,000 bits? I'm planning to use a shake output.
Yes, you can do this. So this is indeed, there is no limitation in that sense. The limitation comes from you need a hash which is long enough, which you can get by using an expandable output function like shake. And then you just have to analyze the security. And of course, you have to look at the performance of force for this case, right? So because as you increase T, your trees go up, like your tree sizes and force go up. And so this makes the whole thing more costly. But this is a trade-off that you can play around with. So if you can save layers in the many-time signature scheme in place of this, this might actually give a more performance scheme. So I think that there is a decent chance that we did not look at every possible trade-off that can be played for the Sphinx Plus parameters.
Okay, thank you. In the interest of time, you should stop here. I've posted on the Zulip channel, so not everybody who registered has appeared on Zulip. I know who you are. On the Zulip channel, you can find a topic social breaks, and on the social breaks, you'll get a link to a Wonder Room where you can now go and mingle and meet. Andy will be there for the next, by now, probably less than 15 minutes because he has to rush off to also catch lunch. But please join Andy there and, each other to ask your questions in person. Then you can also give the thanks and applauses there. I'm seeing the questions on Zulip regarding the proceedings. I'm not on a university network and it's working, no problem. I tried to debug over the lunch break. But for now, thank you very much, Andy, and hope to see all of you in the Wonder Room. Bye-bye.
Thank you.